Well, I apologize for the break. I needed to check that I really got this formula right, that I remembered it correctly. It is in fact correct. Okay, so let's see now what happens as I keep moving some of these points. So if we move, so let's call this point of the intersection of this circle with the x-axis, let's call it P. So if we move A towards P, what happens to this distance? So that means I'm interested in the limit as A goes to P of this hyperbolic distance A over P. So A goes to P along the geodesic, along arc PAB. So what happens to this? So that's the limit. So one of the angles, namely the angle alpha, approaches pi, 180 degrees, right? As A moves towards P, then alpha approaches pi, of natural log of cosecant alpha minus cotangent alpha divided by cosecant beta minus cotangent beta. Okay, so that really concerns the behavior in the numerator. So what's cosecant of alpha minus cotangent alpha? Minus cotangent alpha, that's 1 over sine alpha minus cosine alpha over sine alpha. So that is 1 minus cosine alpha over sine alpha. And now what happens to it as alpha goes to pi over to pi? Cosine of pi is minus 1. So 1 minus minus 1, that's just going to be 2. I mean, the top goes to 2, right? The top goes to 2. But the bottom goes to 0. So this whole thing approaches infinity. So as alpha goes to pi over 2, this limit is equal to, as alpha approaches pi, this limit goes to infinity. So indeed, this geodesic extends indefinitely in this direction. I'll leave it to you to check that if you move B, keep moving B towards this next point of intersection, let's call it Q here, and that limit also gives you infinity. So indeed, you can actually extend a finite geodesic indefinitely in both directions. Again, for us it looks like it's only a finite geodesic, but not to the people who live on the hyperbolic plane. They can never see the x-axis as they keep walking along this geodesic. To us, it looks like they keep walking slower and slower and slower and never get to the x-axis. For them, it's an infinite path. So postulate number 2 holds on the hyperbolic plane. Let's move to postulate 3 now. At every point, there is a so for every point, there is a circle centered at that point. Of an arbitrary radius. So we already know from the previous lecture that hyperbolic circles are the same as Euclidean circles. So sort of the first part of this claim is clear, namely that if I take any point, let's say here, let's call this point HK, then I can draw a circle. I can definitely draw a Euclidean circle So if I now look at the point directly above it, so let this be this Euclidean circle, let's say it's of radius r. So that is hk plus r. And the point directly below it is hk minus r. So let's say, let's call this C. So let C be a Euclidean circle. Let's say be the Euclidean circle. Centered at a point hk on the hyperbolic plane of radius r, so that the circle actually fits into the hyperbolic plane, I need the radius to be less than the y coordinate k. So yes, around every point I can draw a circle. But can I draw a circle of an arbitrary radius? And here again, it seems like that's not possible because this radius is bounded by the y coordinate of the point. However, that's the Euclidean radius. That's not the hyperbolic radius, right? Maybe I should say Euclidean circle of Euclidean radius. Euclidean radius. Okay? So we know that this circle is also a hyperbolic circle. And actually, let's compute its radius. Hyperbolic radius. So we know C is also a hyperbolic circle. So let's compute its center and radius. If you recall, the center, so the midpoint between 2 points vertically aligned from each other, is the geometric mean between their y values. So the center, the hyperbolic center, let's say the hyperbolic center, of C is equal to, well, the x-coordinate is going to be the same, h. However, the y-coordinate is the geometric mean between these two y-coordinates. So it is the square root of the product k plus r, k minus r. In other words, it's h k squared minus r squared. So that means, first of all, that the center, of course, is not that, and it is somewhere closer to the bottom. So this is the hyperbolic center. Let me not write the coordinates here to not make the picture, leave the picture quite transparent. Okay, let's compute its radius. So to compute the radius, it's enough to just compute the diameter, and then I take half of that. So the hyperbolic radius which is half of the hyperbolic diameter, which is 1/2 of the hyperbolic distance between the points hk plus r and hk minus r. But these points are vertically aligned, so I know how to compute their distance, so it's natural log of the ratio of the y-coordinates. So this is now the hyperbolic radius. So the first thing to notice is that this radius actually, if r grows bigger n approaches k, then the bottom goes to infinity, so the radius of the circle goes to infinity. So indeed, so note, as k goes towards r from the left, so it's still smaller than r, then this radius, then 1/2 natural log k plus r over k minus r goes to infinity. So in fact, you can have circles of an arbitrary hyperbolic radius. There's something fishy about this proof, though, because I wanted to say that around every, so that there, given any point on the hyperbolic plane, there is a circle centered at that point of an arbitrary radius. But what I have proved is that given any point on the hyperbolic plane, hk, I can find a circle that has a different center. Because that point here is only the center of the Euclidean circle. It's the Euclidean center of this circle. So how do I know now that starting with any point, starting at any point on the hyperbolic plane, I can actually find a circle that's centered there? Well, that's just sort of solving these equations that are given here for the variables k and r. So, so suppose, let's just put it this way. So where do we have the expression for the radius? So the hyperbolic radius, let's just call it RH, the hyperbolic radius. So if I want a circle of certain hyperbolic radius, let's say RH, and I want the circle to be centered, so want the circle to have hyperbolic center, HK, now this is capital H and capital K. So maybe I shouldn't write this. So let's just rewrite this differently. So suppose I want to construct a hyperbolic circle centered with hyperbolic center HK and hyperbolic radius RH. So I know that such a hyperbolic circle, if it exists, is also a Euclidean circle. So we need to do this, we need to solve the equations that we have here. So first equation is H equal to H. We should say it this way, H equals to H. This is essentially nothing, there's nothing to do. Then the square root of k squared minus r squared should be equal to k. And finally the radius should be 1/2 natural log k plus r, k minus r is equal to RH. So the equations for HKR. What will that give us? So suppose you give yourself HK and some radius, hyperbolic radius. So say, I don't know, H is 1, K is 7, and you want the hyperbolic radius to be 15. So you set up these equations. So H is equal to 5, this one is equal to 7, and this thing is equal to 15. So 3 equations with 3 unknowns, little h, little k, little r. And if you solve them, so when you solve this system of equation, you get these numbers, right? H, K, and R. Now, draw a Euclidean circle. Euclidean. Centered at HK of radius R. And by the calculations we just done, you know that this circle is also a hyperbolic circle whose hyperbolic center is HK and whose hyperbolic radius is RH. Okay, so you would get what you set out to find. You wanted to find a hyperbolic circle with that hyperbolic center and that hyperbolic radius. So I'm telling you how to do it. If these are numbers, if you just give yourself some 3 numbers, you solve this system of equations, you get 3 numbers H, K, R, and you draw a circle center, Euclidean circle centered at HK of that radius, and you know that the hyperbolic center of that circle is exactly this H and this K, because that's the calculation we just did. And what's the hyperbolic radius? It's this. So it's exactly what you wanted. The question is now, do these equations have a solution? And the answer is yes. I am not going to derive the solution here. This is not difficult at all, actually, to derive the solution, but that's just manipulating some formulas. So what are the how do you get the solutions? Well, first of all, the first one's just staring at you there, right? There's nothing to solve. H is equal to H. That's already solved. So it's just these two that need to be done. For little r and little k. And the solutions are the following. You get that r squared is equal to k squared e to the r minus e to the minus r over 2 squared, and k squared is equal to k squared e to the r plus e to the minus r over 2 squared. The one thing to notice, right, is that it's clear from here that k is greater than r, as it needs to be for that circle to actually never cross the x-axis. These things actually have a different name, and it's actually useful for us to know the name of these functions. This is called the hyperbolic sine of r, sinh. hyperbolic sign. And this is called the hyperbolic cosine. So it's cosh of r. And why they are called this, you will see when we study trigonometry on the hyperbolic plane. But to sum up, the third postulate says that given any point I can find a circle centered at that point of any radius that I want. So if you give me a point whose coordinates are hk, and you give me a radius, then how do I find a circle whose hyperbolic center is hk and hyperbolic radius is this? Well, I set little h to be big H, I compute little r and little k from these two formulas, and from that I obtain first of all the little h and little k, so I put the point little h and little k on the plane, on the hyperbolic plane, and then draw a regular Euclidean circle centered at that point of radius little r. And when I do that, I used capital R. What's capital R? That's actually, I'm sorry, the capital R is this. Capital R is the hyperbolic radius. It should have been little rh, right? So this is just capital R. So when I do this, I obtain a Euclidean circle centered at little h, little k of radius little r, and its hyperbolic center is this point I wanted, hk, and its hyperbolic radius is this r, also this thing I wanted. Okay, so the third postulate of Euclid also holds on the hyperbolic plane. Postulate number 4 said that any two right angles are congruent. We haven't yet talked about angles. That's next lecture, so I'm not going to comment on the fourth postulate. However, there's the fifth postulate, the parallel postulate, and here I wanted to discuss this. But instead of discussing the fifth postulate in its original formulation, let's discuss the Playfair's postulate, which says the following. So 5, as a Playfair's postulate, given any line and any point, let's say P, not lying on that line, there is a unique line through P that is parallel let's just call, given any line L that is parallel to L. Okay, right, on the plane it's equivalent to the fifth postulate. This is what it says. If I give myself a point P and a line L, then there is a unique line that goes through P that is parallel to L. Does this hold on the hyperbolic plane? Let's see. First of all, what are parallel lines? We're going to define parallel lines the same way we define them on the plane and on the sphere. These are lines that do not intersect. So, definition, two geodesics on the hyperbolic plane are parallel if they don't intersect. Okay, so let's give ourselves a point and a line. So here is a hyperbolic plane. Let's get ourselves a point, P. And let's give ourselves a line. Let's say let's just take a vertical geodesic here. So, what about, I would like to find a geodesic that goes through P and doesn't intersect that line over there. So that would be my line L. Well, there's one here. That line definitely does not intersect this line L, so it's parallel to it. But here's another one. That's also a geodesic. That's also a geodesic through P. And this geodesic also doesn't intersect the line L. So I specifically took it so that it actually ends here before L. So it's also parallel to this line and also goes through P. And it's not only specific to these vertical lines. I could have drawn my line here. Right? This is also a geodesic, centered somewhere here. And now I take my point P, and if I draw these two geodesics, both of them go through P and none of them intersect this green line. So both of these orange geodesics are parallel to this line, they're also parallel to that one. So, in fact, there are more than one. So the fifth postulate does not hold on the hyperbolic plane. Hence the name non-Euclidean geometry.